Okay, thanks for coming. I'm Juri Lelli. I work at ARM. I've been working in the last 3 years, mostly on the energy-aware scheduler initiative, mostly focused on the CPU freak governor parts and the energy model. Before joining ARM, I actually worked on the SCHED DEADLINE Linux kernel scheduler, and I participated in the project, and then the team got merged, so that's why basically I'm here today. Also, I'll be talking about the ongoing development that we are doing both at ARM and collaborating with the University of Pisa about this. And I don't have much time in this session, so I'll just skim through the new features that we are trying to add to the scheduler, but we have an hacking session in the afternoon, so you are very welcome to come. There will be more time to discuss details. All right, so that's basically what I'd like to share with you today. I'll give a really quick introduction about what deadline scheduling is, and then I'll detail about the new feature that we are developing. Okay, so what's SCHED deadline? What's deadline scheduling? Deadline scheduling is basically an additional scheduling policy and class for the Linux scheduler. It has been merged in v3.14, so it's basically roughly 3 years ago. I guess the main features is that, despite the name, it's not only about deadlines. Why? So, well, it is a real-time scheduling policy like SCHED5 or SCHED-RR. But it's basically, I'd say, more powerful because you can actually explicitly specify per task latency constraints using the new API. So there is a new sys call that has been introduced, and using this call, you have a more rich API to specify these latency constraints. By design, it avoids starvation between tasks, and in general reaches the scheduler knowledge about the quality of service requirements of the different activities that run on your system. It implements a couple of algorithms. The basic one is EDF, which stands for earlier deadline first. It means that you basically prioritize the task with the earliest deadline. And then it also implements CBS, that stands for Constant Bandwidth Server, which is basically the, let's say, is the guy actually basically deciding which are the dynamic deadlines. As I said, I won't enter in detail, so you are free to ask me more questions after this session. There is no time to actually enter into those details. It implements a resource reservation mechanism, and the resource here is, of course, CPU time. And basically implements also temporal isolation between tasks, so tasks belonging to different reservations cannot jeopardize each other activities. There are actually now a couple of presentations. So I given last year a presentation at ELC, and you can find a link there where I actually talk about all the details of the current implementation. And actually I given a longer view of these new features a couple of weeks ago at ELC 2017. So you will also find that information on probably YouTube already. So why we actually decide to try to spend some more time on it? Basically, as part of the energy-aware scheduling work, and also after basically actually has been merged in the Android Linux common kernel, we basically realized that there are still some activities going on in the system that really needs very strict latency. Really needs to meet very strict latency requirements. So what's happening in Android is that for those few activities, we basically started using SCHED5, so it's basically using an RT scheduling policy and class. Things actually works fine, but the problem is that there are a few, I'd say also quite invasive modifications that were required to actually make this thing work for Android. And personally, I guess it's not so easy to see those modifications merged upstream. So the point here is that SCHED Deadline seems to be a better fit, firstly, for those kind of activities. And secondly, the same kind of modification that will be required to actually make it useful, it seems to be easier to defend on the Linux kernel mailing list, so to propose to the maintainers. That's why basically we started working on it again. And actually this activity, it's a joint collaboration between ARM and Scuola Superiore Sant'Anna of Pisa, which is also basically the laboratory which I've been working on during my PhD that actually make this thing, the SCHED Deadline thing possible and upstream. Same guys are ready. Okay, so let's enter into some details. The first new feature that we're actually implementing is called bandwidth reclaiming. What's the problem with the current mainline SCHED Deadline? The problem is that once you use the interface, so this new syscall called SCHED setup, then the bandwidth that you allocated to the task is fixed. So the task has to actually run inside that amount of runtime that you actually allocated to the task. But what happens if the task occasionally need more bandwidth than what he actually requested to the system? Basically, it is throttled, so it cannot actually escape this runtime. So if you, for example, have some occasional workload fluctuations, like due to, for example, network traffic changes, or maybe you're rendering a particularly heavy frame in the rendering pipeline, your task will be throttled. So that might affect the quality of service. So it might affect what the user experience is. To fix this problem, we are proposing a solution that implements this thing called bandwidth reclaiming. We are proposing already this thing also on a mailing list, so there have been at least 4 successive sets posted on the Linux kernel mailing list. There will be probably a V5 of this set of features, hopefully by this week or next week. We are actually finishing the testing of the new set. What it does is basically it gives tasks the possibility to consume more than what they have been allocated at SCHED setup time. By basically, you can specify a certain maximum fraction of CPU time that those tasks can actually reclaim. And of course, this has to still guarantee the temporal isolation. So you don't want that by allocating this more bandwidth to those tasks can actually jeopardize other activities. That's the basics. Yeah, I put here the link to the last Linux kernel mailing list posting. You can find more information there. And that's what the solution is implementing. It's implementing an algorithm called GRAB, which stands for Greedy Reclamation of Unused Bandwidth, which is basically composed by 3 main parts. Again, you can find more information on the papers that I'm putting there. But basically composed by a mechanism to actually track the utilization of the active task on the system. It modifies the SCHED Deadline country rule. The country rule is it's basically the thing that actually enforces the runtime of the running tasks. And then it basically, the implementation actually extends the original GRAB algorithm, because that algorithm was actually designed for uniprocessor systems. But of course, we have to support multiprocessors, so we needed to make some modifications. As said, you're very welcome to come this afternoon. I think it's at 2, right? Yeah, 2 or 2:30 in session 2. That would be the second session. Yeah, just some very easy results. This is all run in synthetics, but just to highlight what's the purpose of this feature. Let's say that in this particular example, you have 2 tasks running on the same CPU. You have one task that is it's a constant execution time task of 5 milliseconds. It is running inside a 6 millisecond, 20 millisecond reservation. This is running together with another task that is 45 millisecond, 260 millisecond task reservation, but the task actually runtime varies between 35 and 52 milliseconds. What I'm showing here is cumulative distribution functions of the response time experienced by the two tasks. How to read this? Basically, you have the response time experienced by a task on the x-axis, and you want, basically you want that the actual response time, you don't want to cross this line, which is the 260 millisecond deadline for the second task. The problem with the current deadline implementation is that since the second task sometimes try to execute for more than the 45 milliseconds that has been granted, is actually throttled. So there is a non-null probability that the task actually have to basically miss its deadlines. Instead, when you enable the bandwidth reclaiming feature, the task can actually reclaim some of the spare bandwidth, so it can complete always before the 260 milliseconds. This is, as I said, a really simple example just to show how the thing actually can be useful. All right. So that is the first set of patches and basically implemented this new feature. Another thing that we actually need is, of course, CPU and frequency scaling. So currently, the reservation parameters are fixed. So when, and basically the assumption is that you always run at the maximum frequency. But of course, if we plan to use this on an Android platform, we actually want to save energy and power by running at lower frequencies. So we need to scale the reservation parameters. How it works? We actually need only to scale the runtime because the period is fixed. I mean, it's frequency invariant by itself. The runtime, I guess the assumption is that we can scale linearly the runtime with the clock frequency. It's an assumption, but it kind of works in practice. And it's similar to what the CFS load tracking mechanism already does. Here are only detailed the formula that we apply to scale runtime considering clock frequency or capacity. Basically, capacity is the translation of the available clock frequency considering at 0, 10, 24 scale, nothing fancy. We apply this formula, so it's basically just multiplying the original runtime by the ratio of the max capacity in the current capacity, and that gives you that bit more of runtime to actually complete still in time. We apply this for frequency, and we then have to apply basically the similar formula for CPU invariance. If you're running for example, in a big little system, when you have different max capacity for the different CPUs. It's the same thing, again, that Pelt is doing already. Yeah, I have an additional couple of slides detailing how this thing actually works in practice on, for example, I run some experiments on an iKeyboard, and again, I can show you these bits in the hacking session. So again, come. All right. Now that we have frequency and CPU scaling, we actually want to drive frequency, because basically what's in mainline today with the SCHED governor, it's only considering, let's say it considers the utilization requirements for the CFS tasks, but then when you have either real-time or deadline tasks, you just go to max. And that's, of course, not optimal, let's say. So you want something better. The idea is that you need to scale clock frequency, but still you want to meet task requirements. So you cannot actually scale too much. As said, SCHED normal we use is util average, which is the Pelt signal. and then currently FIFO deadline go to max. So the plan is once the bandwidth reclaiming set is going to be in, so it's accepted in the Linux kernel, then we can start adding up the SCHED deadline per CPU utilization contribution to the CFS utilization contribution, and then come up with the, summing up the two is basically considering both utilization requirements. We'll have also to move the places in the SCHED deadline schedule where we actually trigger OPP requests. Again, too much details. The fact is that currently we trigger on a tick boundary, but it doesn't really make sense for deadline just because the algorithm works differently. So we need to change that. It's not an invasive change. I guess out of the three, the most probably controversial one will be the fact that for a platform that actually might require to sleep for changing frequencies, like in ARM systems, the SCHED util CPU flag governor is currently using a K-worker to actually do the job. This K-worker currently is scheduled by SCHED FIFO, but of course, if you need to change frequency for SCHED deadline tasks, you want that guy to actually be able to preempt SCHED deadline activities to actually change the frequency. So we'll need to make it SCHED deadline. Problem is that what parameters then you associate to the task, which deadline runtime. The current solution that I got is that I basically treat that guy as a special deadline task which preempts everybody and can actually change frequency. Maybe it's acceptable, maybe not. We'll have to discuss this thing on the mailing list again. Again, hacking session, more details. Oh, and by the way, this Claudio Scordino working for Evidence, which is a startup of Scuola Superiore Sant'Anna del Pisa, is helping with those bits. I just want to mention this. Okay, so last part of the series, group scheduling. Currently, SCHED deadline doesn't support group scheduling as CFS and FIFO do. So basically, currently we have a one-to-one association between tasks and reservation. You cannot group set of tasks inside the same reservation. But sometimes it might be better or easier to actually do this kind of association. For example, you can principal think to run virtual machine threads on the same reservation. Or if you have a rendering pipeline, you might want to reserve a fraction of CPU time to the whole pipeline or set of tasks of the pipeline. You might need to support legacy applications which don't actually, which the source code of cannot be modified, so you might want to support that as well, and other possible usages. So what we are actually implementing is called a hierarchical group scheduling. There is, again, a lot of theory, RT scheduling theory behind this, so we are actually implementing one of the possible alternatives. More details in the papers that I'm detailing there. The idea is that, you can basically group a set of tasks in the same reservation, then you actually enforcing temporal isolation between such groups. It's basically extending the one-to-one idea to group of tasks. How it would work, it will mean that basically at the first level, so at the root scheduling level, you will be using EDF to actually know which one of the both groups and leaf entities you have to schedule. And then inside the, let's say that you have a group of tasks, inside you first select the entity, and then inside you actually selecting which one of the tasks using FIFO. So it will be a double two-level type of approach. I guess the plan, well, Peter Zijstra, often I talk with him, and basically the plan is once we have this thing implemented, we can basically supplant the current R3 throttling mechanism, which more or less does the same, but is less powerful. So it makes probably sense to switch to use this. how it will be implemented in practice? In practice, basically, for each group, you will be able to specify, again, a runtime, deadline, period, set of parameters. And basically, you have to imagine that those parameters will be replicated on all your CPUs. So you will be having basically one SCHED deadline entity representing the group on each CPU. And then you basically put all your FIFO tasks inside those per CPU reservations. And of course, they can coexist. So here I'm basically plotting. This is a group entity, but this is like, it's actually a pure SCHED deadline entity, so it's actually a task. So the two can actually coexist. Of course, when you migrate the FIFO task using the RT push and pull mechanism, those tasks will be actually migrated between these SCHED deadline entities. So the SCHED deadline entities corresponding to a group can be thought of like virtual CPUs. Yes? Yeah, so currently it's one. For all, you have just a couple of values, and basically that amount of bandwidth will be replicated on all your CPUs. Yeah, I mean, the implementation is per CPU, of course, but then from a user space point of view, you will be having one single value. Yeah, of course. Again, yeah. All right. So that's basically covering all the features. Yeah, we're in time. And what's missing? Well, let's say that there is still some work to be done that we are not currently doing. Currently, I'm experimenting on Android. I've been doing experiments using the iKeyboard. I recently actually managed to backport all the 318 mainline set of fixes that applies to deadline on top of the Pixel phone baseline, so we can actually most probably play with these features on a real platform, commercial grade platform. That's good. In the near future, I guess, once we implemented those features, we might want to extend the reclaiming idea by basically implementing the motion towards a lower priority class. What it means that you can think in principle that instead of throttling your task, you can actually demo them, so let them run, continue running on, for example, using CFS until the next period. That will help meeting the deadlines. Then, of course, we'll have to implement capacity awareness because you actually have to run on big little systems. So we need actually to be aware that there might be maximum capacity, different maximum capacity on the different CPUs. And of course, then we'll have to use the energy-aware scheduling energy model and see how we can actually save additional energy, coupling the information that we now have in the kernel side with the energy model description of the platform. This is all near. The near-ish means that nobody's actually working on it currently, so you're more welcome if you're interested to actually start working on these things. We basically have to refine the CPU affinity requirements for deadline. I won't enter into details, it's just the fact that currently you cannot set an affinity closer to basically the system, or at least the root domain associated to a group of tasks for deadline. Then we'll have to enhance priority inheritance. What we have right now, it's only deadline inheritance, so you're actually inheriting the deadline when you're boosted because you actually hold in an RT mutex, probably implementing a multiprocessor bandwidth inheritance mechanism. And then might be also something to work with, like a dynamic feedback mechanism, so a possibility to have a way between user space and kernel space to actually constantly have a feedback on how things are going in kernel space and adapt to possible needs. All right, that's basically what I've got for today. If you have more questions, shoot me an email, shoot an email on Linux Kernel email list, RT users, ES dev, we are all on all those lists. And please come to the hacking session. And actually, we are putting together a summit, a workshop summit in Pisa next month. So it will be 3 and 4 of April. So you're more welcome to join us. We'll be discussing this thing, but also energy-aware scheduling, power management, and all sort of kind of stuff. So that is interesting, I think. Thank you. If you have questions, I think we have some. Probably still 5 minutes for questions if you have any. Yeah.
So is only a 2-level hierarchy supported or even more levels?
So currently what's implemented in the patches that we have is only 2 because it's difficult to understand how you would use more than 2 levels. So we just started simple, I guess.
As far as I have seen, usually the way to define the service properties that you want to give to groups using group scheduling is by always using groups. So I mean, even if you have only one task, and for example, you want to decide the bandwidth to give to that task, you wrap it in a group, and then define the bandwidth or whatever for the group. Why didn't you use the same common approach?
I guess to get this thing actually merged, the easiest solution was actually not taking into account groups from the start, because it actually complicates things. So that
Now, because you have a single task.
Well, you can once you have group shell, you can actually do like what you're proposing. You can create a group and then put your FIFO task inside it. That will be like the same as using the SCHED setup with a single task. You can actually do that, yeah. Actually, it will be, it's probably solving, I mean, your approach is probably solving the problem that we have with when the task forks and it's a deadline task. So currently it cannot fork because we don't have a way to actually give share the bandwidth among the children and parent. So there might be a way to solve this issue. Yeah. Other questions? All right. So see you later.